All right, so dealing with uncertainty, we're going to talk about error types. We're also going to talk about things like significant digits. So it might have been a while. I think in chemistry, you do a lot of significant digit stuff, but I don't know what your experience is with it. So don't worry, I won't expect that you know what significant digits are. We will completely define them, and I'll give you all the rules for them as well. All right. So we'll start with that. Significant digits are the digits in a number that represent actual measurements. And it says we can use scientific notation to avoid any ambiguity in significance of trailing zeros. That may not make too much sense right now, but we'll do a couple examples and hopefully it will make sense at that point. So one quick example, right? So if you weigh yourself on a scale and it says 175 or whatever, while it's true that 175 and 175.00 are equal, they have a different number of significant digits and they communicate different things. 175 says we're being precise only to the nearest unit, right? Only to the nearest pound. Whereas 175.00 indicates that we are measuring to the nearest hundredth, right? So this has 3 significant digits. This has 5 significant digits. And significant digits just indicate how precisely we are measuring something, okay? So even though those are equivalent values, their precision is different. All right. So let's see. Here's a table that indicates what is a significant digit and what is not a significant digit. Anything that's non-zero is always considered significant. Zeros that follow a non-zero digit and lie to the right of a decimal point are always significant. So that was like in my weight thing. If it was 175.00, that's indicating that we are measuring to the nearest hundredth. So those zeros are significant because they're telling us how precise we are measuring. Any zeros between non-zero digits are also always significant. So like these 2 zeros in 4002, those would be significant. Or this 0 in 3.06. That's also always significant. Or if it's a 0 between another significant 0, meaning like this 0 between the point 0, that's a significant digit. All right, so what are not significant? Zeros to the left of the first non-zero digit. So for example, this number has 1 significant digit. This value, the 0.00052, has 2 significant digits. And then any 0 to the right of the last non-zero digit, but before the decimal point, are not significant unless stated otherwise. So again, this 40,000, that has 1 significant digit. This 210, that has 2 significant digits. Okay? All right, so this table is there, and these slides are posted as a PDF as well, so you can have access to that. But But let's just get some practice. I want you to try and participate in the chat. I'm going to ask you how many significant digits certain numbers have, and you can tell me in the chat. All right. So a time of 11.90 seconds. In the chat, how many significant digits would 11.90 seconds have? Four. Good. I agree. So all four of those are significant, and the meaning is that we are measuring to the nearest hundredth. All right. What about B, a length of 0.000067 meter? Good, I agree. Two significant digits. In that case, even though there's only two, we're still measuring to the nearest, what is that? Tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths? Ooh, okay, what about C? How many significant digits do we have there? I agree, two significant digits. Just these two, right? In that case, we're measuring to the nearest 10,000th. Of a gram. How about D in the chat? How many significant digits? Sorry, I had to let the dog in. Agreed. Still just two. All the trailing zeros are non-significant digits, so 2. And this is being measured to the nearest 10,000 people. What about E, last one? Yeah, good. All in scientific notation, anything after the decimal that's going to be considered significant. So 3. And it's the same number as part D, so the meaning is the same. We're measuring to the nearest 10,000 people. Great, good work. Okay, just a quick review on how to round appropriately. It's a 2-step process. So step 1, decide which decimal place is the smallest that should be kept, and we'll talk about how to make that decision. So there's some rules to that when you're dealing with significant digits. But first, make that decision. What's the smallest decimal place that should be kept? Then step 2, look at the number next in the next place to the right. If the value in the next place is less than 5, they say round down. I don't like that because you're not really doing that. You're just truncating, meaning you're just chopping the decimal. If it's 5 or greater, then you do round up. So what I would say is, like, let's say I'm trying to round 2,347, and I want to round it to the nearest tens. So I want to round it to this decimal place. So then I would look at the number to the right. It's a 7, so I would round it up, right? So that would round to 2,350. All right, well, let's do another scenario. Let's say we were instead rounding to the nearest hundreds. So I want to round it to this decimal place. I look to the right. Oh, it's less than 5, so I just chop it there and replace it with zeros, right? All right. So most of you have some experience with rounding. I just wanted to do a quick review. Okay. Again, let's do this in the chat. Get some interactivity here. So A, I want you to round this one to the nearest thousands for me. I'm sorry, thousandth, I should say. All right, so let's see. The nearest thousandth, that's the 9. So we look to the right, it's a 3. That's less than 5, so we would just chop it off. So that's 382.259, and we're done. Good. All right, now let's go to the nearest hundredth in the chat. Good. So now we're trying to round to that decimal place. So we're looking at the 9, which is greater than or equal to 5. So it's 382.26. Tenth. $382.3. I agree with that. So we're rounding to here. We're looking at the 5. Ones place. Good. Just 382. So we would look at this too. Tens. 380. Awesome. And then hundreds. Last one. 400. Perfect. Great. Good work. Okay, so you can grab a calculator. We're going to do an example, and then we're going to round to the specified number of significant digits. So 7.7 millimeters times 9.92. So if I just multiply that out, that's going to give me 76.384. But we only want 2 significant digits. So the only 2 significant digits we will keep are the 7 and the 6, which means we need to round to the ones place. So this just becomes, we're paying attention to the 3. That just tells us, okay, truncate. So 76, and then our units, millimeters times millimeters, would be square millimeters. Oh, with this lag, here's where I start to lose it. Come on now. There it is. God. All right. 240,000 times 72,106, and we want our answer with 4 significant digits. So just multiply that out in your calculator. All right, so what we end up with, your calculator should be giving you scientific notation. 1.730544 times 10 to the 10th. And if I want 4 significant digits, I will round it to the thousandths place, which means I'm paying attention to the 5, and I'm going to rewrite it as 1.731 times 10 to the 10th. All right. Let's keep moving. All right, I'm going to give you a second to copy these down because these are definitions you need to know. There are two types of errors. There are random errors that occur because of random and unpredictable events in the measurement process. And then there are systematic errors where there's some problem with the measuring system itself, and so it's affecting all measurements in the same way. Okay? So the example I like to give of this is like me grading a test. A random error would be I'm not paying close enough attention and I maybe mark one on yours wrong when it was right. And I just accidentally did that, right? That's a random error. A systematic error would be if my answer key, one of the problems in my answer key was made incorrectly, right? So my answer key says B when the answer is really D. That's a systematic error because I'm going to be marking everybody's test incorrectly. Whereas the first one was just a random error. I just wasn't paying close enough attention when I graded your specific test. Does that make sense? This is the example our book gives. I don't like it as much, but it kind of illustrates it. The baby, like if you're trying to weigh a baby and the baby's moving around on the scale, that might cause the numbers to jump. Those would be considered random errors. But if you remove everything from the scale and the scale is still reading 1.2 pounds, that means it's miscalibrated and it's going to overweigh everything that you put on it by 1.2 pounds. So that's systematic. There's something wrong with the measurement tool versus this is random. All right, let's talk about absolute error. So absolute error describes how far a measured value is from the true value. And so to find absolute error, you take the measured value, you subtract the true value. And then relative error compares the size of the error to the true value. So relative error is a percentage. You take the absolute error and you divide by the true value. All right, so let's do an example where we find these. So a projected budget surplus of 17 billion turns out to be 25 billion at the end of the fiscal year. So in this case, the projection is going to be our measured value, and then what actually happened is going to be our true value. And that may seem weird because it's not a measurement, it's a projection, but it's easy enough if you just figure out what the true value is first, then the other one has to be the measured value. All right, so to find the absolute error, we'll take the 17 billion and we'll subtract, 17 billion and subtract the 25 billion. That's going to give us negative $8 billion in absolute error. All right, and if we want to convert that to relative error, we'll just take that negative 8 billion and we'll divide by the true value of 25 billion. Since these are both billions, that's fine. And then we'll multiply it by 100 to get it as a percent. And so what we end up with is negative 32%. And the negative just indicates that it was an error on the low side, right? It was under projected. If our error was positive, it would be over projected. A few more definitions. The difference between accuracy and precision. Accuracy describes how closely a measurement approximates a true value. An accurate measurement has a small relative error. Precision describes the amount of detail in a measurement. So accurate is how close are you? Precision is how detailed are you? How many decimals are you taking your measurement to? L, is that the go back signal or the slow down signal? Yeah, no problem. I'm sorry. They they uh they messed with my Zoom messed with my green check, so now they just auto go away, and it's really screwed up my pacing because I can't tell if I have you guys use the green check, then some of you put it early and then they'll go away, and I can't tell who's done when. But I appreciate the feedback, and I will go slower. Okay. So with that in mind, we're going to talk about how we're going to combine measured numbers. So when I say combine, I mean add, subtract, multiply, and divide. And then what the rules are for rounding those to make sure that we are not giving more precision than we should have or less precision than we should have. So for addition and subtraction, we want to round the answer to the same precision as the least precise number in the problem. So this is kind of a chain is only as strong as its weakest link, right? In addition and subtraction, your answer can only be as precise as the least precise number involved. For multiplication and division, it's similar, except we're going to base it on, instead of precision, we're going to base it on significant digits. So you have to round the answer to the same number of significant digits as the measurement with the fewest significant digits in multiplication and division. And then, just to be clear, you only ever want to round after you complete all operations. You never want to round during like intermediate steps, only at the very end. If you round in the middle somewhere, you're going to end up with what we call round off error. All right. So addition and subtraction, we pay attention to precision. Multiplication and division, we pay attention to significant digits. A book written in 1985 states that the oldest Mayan ruins are 2,000 years old. How old are they now? All right. Well, how long ago was 1985 in the chat? How many years has it been since 1985? All right, so 36 years. So basically what we're trying to do is take this 2,000 years and add 36 years to it, right? So this is addition, so we're going to pay attention to precision. All right, so which is the least precise number? 2,000 or 36? So 2,000 is being measured. 36 is more precise than 2,000 because 36 is being measured to the ones place. But again, the zeros after the 2 in 2,000 are not significant, right? So 2,000 is only being measured to the thousands. Whoops, I can spell thousand. To the thousands place, right? So this is less precise. Okay? Which means by the rules that we had for addition and subtraction, we're always going to round our answer to the least precise number in the problem, which means in this problem we need to round to the thousandths place. So I'd add 36 to it, and I get 2036 years. And then I would round to the thousandths place. What does that round to if I'm rounding to the thousandths place? Help me out in the chat. Still to 2000. That's exactly right. So we kind of went in a circle there. And a book that was written 2,000 years ago, a book written in 1985 states that the oldest Mayan ruins are 2,000 years old. We would still consider them to be roughly 2,000 years old. Naomi, in what circumstances is rounding not appropriate? Well, it's always appropriate. It just depends. You just have to follow these two rules, right? So for addition and subtraction, round when you're combining, round to the least precise, to the same precision as the least precise number. And then multiplication and division will round to the number with the fewest significant digits. All right, so let's look at a couple more examples of this. Hopefully it'll help you to clarify that. A government in a town of 82,000 people plans to spend $41.5 million this year. Assuming all this money must come from taxes, what is the average amount the city must collect from each resident? So we want to do a division here, basically. We have 82,000 people. And we want to divide that by the amount of money, so that's 41.5 million, so $41,500,000, right? And that'll tell us what, I did that division the wrong way. I'm sorry. Other way around, folks. $41,500 divided by the 82,000 people. And that'll give us units of dollars per person, right? So how much every person has to pay on average in taxes. All right, but this is a division, so we want to round to the number with the fewest significant digits. So how many significant digits does the 41.5 million have in the chat? Good. 3 significant digits. How many significant digits does the 82,000 people have? 2 significant digits. So we will be rounding whatever our answer comes out to the fewest. So that we will be rounding to 2 significant digits. All right, so let's do the division in our calculator. I'll do 41,500,000 divided by 82,000. All right. And so what we end up with is 506.097561. So if we were to report that answer, it would make it look like we have much more precision than we actually do from these numbers. And so the rule for multiplication and division says round to the measurement that has the fewest significant digits, which for us was 2 significant digits. So I want to round it to these 2 significant digits. It looks like I'll be rounding to the nearest tenth. So rounding that off to the nearest tenth is going to give me $510 per person. Any questions on that one? All right. That's it. So here's what I want you to do. I'll put you into breakout rooms to start working on the problem set. The first thing I would have you do is go ahead and